Alright, welcome back everyone. Let's start off jumping straight into problem 4. So, suppose that a spherical star spinning at an initial angular velocity omega collapses to one half of its original radius without losing any of its original mass. We're going to assume uniform density before and after the collapse with regard to the star, of course. What will the angular velocity of the star be after the collapse? And our options A are omega over 4, B omega over 2, C omega, D 2 omega, and E 4 omega. So let's start off with the concepts that this problem is dealing with. So um, we're clearly looking at angular momentum here. So let's start off with writing down the equations we know for angular momentum. That's always a good starting point. So we know angular momentum is equal to moment of inertia times angular velocity. We also know it's equal to mvr sine theta. And here, one of the key parts of this problem is that the star is collapsing to one half of its original radius without losing any mass. So that just kind of gives me a little bell in my head to think of I, our moment of inertia, because I is essentially equal to mass times radius squared. For different objects, of course, there's different coefficients here for m, but it's going to cancel out anyway because of the conservation of angular conservation of angular momentum. So conservation of angular momentum is going to say that before the stars collapse, that angular momentum is going to be equivalent to the angular momentum after the stars collapse. So basically we know m is going to cancel out either way. We can just write this as just screw it, m is going to cancel out because this will be mr squared. So mass 1 and mass 2 are the same. So r1 is equal to mr2 squared times this. Masses cancel out right away, we know that. Now let's look at the radius. So initially the radius is just r. After, radius is 1/2. So r1 squared, and then after it's going to be 1/2 r2 squared. And when you square a half, it becomes 1/4. So let's move it up here just for convenience. Again, I apologize for my horrendous handwriting. So we know that these are equivalent, and we know that this value is 1/4 of this value. So to compensate, our angular velocity omega is going to have to make up for this being smaller by a factor of 4. So another way to say this is we're solving for our angular velocity of the star after the collapse. So we can say, well actually this is R2. Yeah, no, excuse me. So here, let's look at my error. Let's learn from my mistake. So here I'm writing the radius of the star after the collapse in terms of what it is before the collapse because we know that it's 1/2 of the original radius. So this, I can just keep this as 1, keep this written as 1, keep this written as 1. That makes sure we don't have an additional variable to complicate things. And then we can multiply by 4r1 squared. So to get rid of this, so we can say times 4r1 squared. You got to do the same thing to both sides. or we're multiplying by, oh my gosh, my goodness. Let's just keep it simple. So dividing by a fourth is the same thing as multiplying by 4, and these are going to cancel out. So we end up with 4 is equal to our final omega. So this is basically our answer. What will the angular velocity of the star be after its collapse? It's going to be 4 times its initial angular momentum, because that makes up for the radius, or the coefficient of r squared being 1/4 of what it originally is. So here's our answer. That matches up with E. There's our answer. Thanks for watching. Let me know if you have any questions. Alright, check back in for number 5. Thank you, guys.